Okay, let's dive right into this explainer. Today, we're going to demystify exactly how top-tier Ensemble models actually work under the hood. We are tracing the absolutely fascinating evolution of machine learning, starting from the foundational logic of AdaBoost all the way to the massive, paradigm-shifting power of gradient boosting. If you've ever wondered how these algorithms can take super simple rules and combine them to create unbelievably accurate predictions, well, you are in the exact right place.
Here's our roadmap for this explainer. First, tuning your AdaBoost model. Second, AdaBoost start to finish. Third, why we needed better. Fourth, the mathematical compass. And finally, number 5, gradient boosting step by step.
All right, let's kick things off with section 1, tuning your AdaBoost model, mastering the hyperparameters.
To really understand this, let's look at a classic case of diminishing returns. Check out this table from our Wildfire PM 2.5 data. It brilliantly illustrates how adding more estimators, our weak learners or decision stumps, dramatically improves accuracy at first. Like jumping from 20 to 100 estimators bumps our accuracy from 90 to 95%. That is a solid leap. But look at what happens when we crank it all the way to 500 estimators. We hit a massive wall. Computation time literally explodes for a tiny, almost unnoticeable 0.4% gain. So the goal here isn't just throwing as many estimators as possible at the problem. It's about finding exactly as many as necessary to strike that perfect balance between accuracy and efficiency. Now, our second vital lever is the learning rate, which controls how much influence each of those weak learners has on the final model. It's actually a lot like painting a wall. You could slap on one really thick coat quickly with a large learning rate, like 1.0. Sure, it's fast, but you're risking a pretty sloppy, unstable finish. Or you can apply many thin coats with a small learning rate, say 0.1, which takes longer, but gives you a highly stable, beautifully refined finish. And here's the catch. These two levers work together. If you drop your learning rate, you are generally going to need to bump up your number of estimators to get that perfectly refined learning.
Moving right along to section 2, AdaBoost, start to finish, the complete blueprint.
So, how does this actually come together? Well, this sequential cycle is the absolute heart of AdaBoost. It kicks off by treating every single piece of data equally. Then, it trains a simple weak learner. Based on how well that learner performs, the algorithm calculates an alpha score, which is basically a measure of trust. How much influence should this specific learner get? But step 4 is where the real magic happens. The algorithm constantly shifts its attention to the most difficult observations by increasing their weights. It's exactly like a teacher giving extra focused attention to the students who are struggling the most. Then, it just repeats the cycle, with the next learner hyper-focused on the mistakes made by the previous one. Finally, the whole shebang comes together in a weighted vote.
But here is the crazy part. The very thing that makes AdaBoost so powerful, that hyper-focus on difficult cases, is also its Achilles heel. It makes the model incredibly vulnerable to noisy data and severe outliers. Imagine a wildfire dataset where a sensor glitches and records an impossible wind speed of 850 kilometers per hour. AdaBoost doesn't know that's a glitch. It just sees a really difficult observation. So it's going to blindly increase the weight of that crazy outlier over and over again, wasting massive amounts of computational time trying to learn a pattern that, frankly, doesn't even exist.
Which brings us to section 3, why we needed better, the paradigm shift.
Because of those fatal flaws with bad data, and honestly a real struggle to adapt elegantly to numerical regression problems, researchers realized we needed a fundamentally better approach. The evolution of boosting had to take a massive leap forward. And it all started with this one question. How do we reduce the remaining error without obsessing over who simply failed? This question single-handedly changed the entire landscape of machine learning. It shifted the focus away from that binary pass-fail mentality. See, AdaBoost looked at predictions as just correct or incorrect. But in the real world, especially when predicting things like exact temperatures or precise PM 2.5 concentrations, we absolutely need a model that understands degrees of error.
So, the crucial concept to grasp here is residuals. A residual is, quite simply, exactly how wrong a prediction is. Instead of just saying our archery shot missed the target entirely, a residual tells us, hey, you missed exactly 5 centimeters to the left. By knowing the precise distance and direction of the miss, our next shot, or in our case, our next algorithm iteration, can be incredibly precise.
Notice the massive shift in philosophy here. AdaBoost focuses on misclassified examples, essentially asking who failed. But the hero of our story, gradient boosting, focuses purely on prediction errors, asking exactly how much error still remains. Gradient boosting doesn't just try to replace a bad model, it purposefully trains subsequent models to specifically edit and fix the exact residual mistakes left over by the previous ones. It's a total game changer.
Let's dive into Section 4, the mathematical compass, navigating the errors.
Okay, so to actually fix those residual errors, gradient boosting relies on a mathematical compass to guide its way. It needs a reliable way to measure its mistakes and know exactly which direction to go to fix them. Enter the loss function. Think of the loss function as our scoreboard. It is the ultimate objective the algorithm is desperately trying to minimize with every single new step. If a prediction is perfectly accurate, the loss is 0. The worse the prediction, the higher the loss. It acts as the absolute judge of how our model is performing at any given moment.
And because gradient boosting is so incredibly flexible, we can actually swap out our loss functions depending on our specific goals. If we're predicting a continuous numerical value, like a wildfire's exact temperature, we use mean squared error, which heavily penalizes large numerical mistakes. But if we're dealing with a binary category, like simply predicting wildfire versus no wildfire, we swap our scoreboard to log loss. Log loss aggressively penalizes the model if it makes an incorrect prediction with high confidence. That kind of adaptability is a massive upgrade over AdaBoost.
Now, if the loss function tells us that we're wrong, the gradient is the crucial tool that tells us exactly which direction to step to become less wrong. It measures how quickly the loss is changing. Without the gradient, the algorithm would just be throwing darts in the dark, randomly guessing and hoping to accidentally stumble upon a better prediction.
Honestly, you don't even need advanced calculus to understand a gradient. Just picture this: a blindfolded hiker trying to navigate down a steep, foggy mountain to reach the lowest valley, the valley of zero error. The hiker can't actually see the destination, right? But by feeling the steepness, the gradient, under their feet, they know exactly which direction leads downhill. Gradient boosting makes these purposeful, mathematically guided corrections, stepping down the mountain of error until it reaches that flat, beautiful valley of perfectly accurate predictions.
Finally, Section 5, Gradient Boosting Step-by-Step, the masterpiece. Armed with our residuals, loss functions, and gradients, we are finally ready to build the gradient boosting masterpiece from start to finish. Let's see how this incredible algorithm operates in practice. Notice how fundamentally different this is from AdaBoost. We start with the simplest possible prediction, usually just the average of all our data. Then we calculate the residuals. We ask, how far off is that average from the truth? And here is the absolute genius part. We aren't predicting the original target anymore. No, we are training new, small decision trees exclusively to predict and correct those remaining residuals. We scale that correction using our learning rate, update our prediction, and repeat. With every single cycle, the residuals get smaller and smaller. Looking at this wildfire PM 2.5 data, you can literally see the magic happen. Let's say our initial prediction for everything is 60. For fire A, the actual is 80, leaving a massive residual of plus 20. Our first tree targets that specific error, suggesting a correction of plus 18. We add that to our prediction, and boom, our new prediction is 78. We just knocked out the massive residual errors, leaving only a tiny manageable mistake of plus 2 for the next tree to gently refine. It's exactly like a sculptor chiseling away massive chunks of marble first, and then using finer and finer tools to perfect the tiny details. So this leaves us with a pretty provocative thought. If this core logic is so flawlessly structured, just imagine the world-changing power it achieves when fully optimized. This exact error-correcting philosophy is the beating heart of XGBoost, LightGBM, and CatBoost, the algorithms that absolutely dominate modern machine learning today across medicine, finance, and science. Gradient boosting didn't just improve on AdaBoost, it literally provided the ultimate blueprint for the future of artificial intelligence. So what complex problem would you want to solve with it?